Hello, this is Dr. Kozhanov again. This is Magnetism and Magnetic Materials Introduction course, Physics 4720, taught at Georgia State University. So this is not lecture 2 again, but this is online lecture 2, which means that this is a lecture coming after the break. The first part of the lecture is I taught in class, using normal whiteboard and interacting with you guys. Okay, anyway. So this lecture is dedicated to antiferromagnetism. We spoke about ferromagnetism, so we will continue and talk about antiferromagnetism. And to start this, I will start with Curie Weiss theory review. Okay, this software allows me to control what I'm typing. So, okay, Curie Weiss theory or Curie Weiss theory review. So, a review. In this review, so what we'll start with, if you remember, we looked at the Curie Weiss law. So Curie Weiss law, the magnetic susceptibility is equal to Curie constant divided by T over theta. Theta is the Curie temperature, C is Curie constant, T is temperature. So if we plot it as a function of temperature, then what we can see is, I'm using this fancy tool to draw coordinate axis. So we have Curie temperature, which is right here. This is susceptibility, temperature, and the curve would be going something like that. So as you remember, this is a paramagnetic state, and this state can be ferromagnetic or antiferromagnetic, so I will write ferromagnetic, but it's an example. This is Curie temperature. Okay, so if you look at this curve, and by the way, this Curie Weiss theory, this is a review. And if you look back, so it's a review. If you look back in your lecture notes on paramagnetism, oh, that's interesting how this software makes triangles out of what I write. So if you look in your review lectures of paramagnetism, then you will see we learned about Curie theory and Curie Weiss theory. So in a paramagnetic state, it's a totally random magnetization oscillations. And as we cool down, the thermal energy, KT energy, becomes smaller and smaller. And at Curie temperature, it becomes comparable to the energy of interacting magnetic moments. And at this point, if you cool down below, then interaction would be stronger than thermal fluctuation energy derived supplied by temperature, and we start seeing basically ferromagnetic ordering. So in a ferromagnetic state, that might be spins of magnetic moments that point in the same direction, but it can be antiferromagnetic, and in this case, oh, this is interesting that software tries to make lines of what I draw. Okay, anyway. This is the antiferromagnetic state, which we'll be discussing. So, if you look at the reasons why we have this Curie temperature, and what is this Curie temperature? As we discussed, there is certain magnetic interactions that result in having non-zero Curie temperature. And Weiss introduced a parameter called molecular field, and molecular field was introduced to, I will be using HM, and we introduced it as gamma M. Gamma is the molecular field constant. So basically, it is an internal field proportional to the magnetization of material. Now, if you I'll be scrolling down. The interesting part about that, so you see that if you look at the temperature here, dependence, temperature is right here. Temperature is susceptibility is basically inversely proportional to temperature. So what we can do is let's rewrite this Curie Weiss law. I will leave molecular field here. Okay. So we can write that if we invert it, we will see that C Curie constant over susceptibility. No, it's not right. Okay, let me go back. So what is that we have here? Yes, that's right. Curie constant over susceptibility would be equal to T minus theta. And from this, you see that if we plot, we can write it in the way that 1 over susceptibility is equal to 1 over C, sorry, not chi. This is 1 over C T minus theta divided by C. So you see, 1 over susceptibility should be linear as a function of temperature. So what it means is that if you have a material and you make susceptibility measurements as a function of temperature, then 1 over chi as a function of temperature should be a straight line. And that straight line basically would go here to the Curie temperature. Okay, so that's quite handy. And we can see that if you plot it this way, it is much easier to plot a straight line and approximate a straight line. Now, what I would do is this. Let's look at this plot. So actually, susceptibility can be positive, susceptibility can be negative. You can remember that for diamagnet, susceptibility is negative. So if you were to measure, let's say, something like sodium chloride or rock salt, you will see that that would be almost independent of temperature. So that would be sodium chloride. This is a diamagnetic material. Then for material like, let's say, manganese chloride, our theta would be greater than 0. So Curie temperature is greater than 0. If you would measure something else, it might be that you would have a curve in the scale of 1 over chi versus temperature. You'll have a curve that doesn't go to 0 within the temperature range measurements. So this is an example for, let's say, iron sulfide, iron SO4. So in this case, the Curie temperature can be less than 0. We'll discuss that. And basically, less than 0 implies that if you extrapolate that, you'll get to your negative Curie temperature in this case. All right. So if you look at these possibilities, then you will see that if theta is greater than 0, let me scroll up and remind me. Remember, we discussed molecular field. So molecular field is something that basically defines the internal ordering. It's an effective field. There is no field, but it's an effective field that can be used to describe the interaction. So if theta, Curie temperature, is greater than 0, that means that molecular field basically is aiding. Let me type these things, so but it would be small. Let me increase the font. So for this case, molecular field aids external field. And in case of theta less than 0, that would mean that we have to basically our molecular field is opposes external field. Okay, so we can have internal molecular field, and a molecular field that is we are talking about that HM that we had above. So this HM is a molecular field. Okay, so molecular field can help in magnetic ordering, or it can oppose external field to get ordering. So if we measure susceptibility, we have to apply small external fields to do that and to measure the response. Or it can be done in zero field as well. But basically, molecular field is you can think of it as an effective force that either aligns or misaligns magnetic moments in material. And again, we already know that there is a magnetic interaction between magnetic moments, and that is something that defines the ordering. But let's stick with molecular field. So now. Let's see. So we studied ferromagnetism. Ferromagnetism. And in order to describe ferromagnetism, first of all, we use base theory, and also in addition to that, we can use Langevins theory of localized moments. So if you remember, Langevin theory is the theory, and we introduced Langevin function in paramagnetism. So if you recall, we also plotted that describes the magnetic interaction, and if we plot magnetization of material as a function of temperature, then at zero temperature it is in ordered state, but as you increase temperature, it would go down to 0, and this is a Curie temperature. That's Curie temperature. So above that we have a paramagnetic state, below that we have a ferromagnetic state. Ferromagnetic state exhibits non-zero magnetization, so but as we increase temperature, the thermal fluctuations kill they do not kill the interaction, but they overcome the interaction, and we have a totally random paramagnet. Okay, so now it is important to indicate that magnetic moment per atom would be different in paramagnetic and ferromagnetic states, because in paramagnetic states there is no interaction. In ferromagnetic state there is interaction. So ferromagnets, there are different materials. So for ferromagnets at room temperature, we know that there is iron, nickel, cobalt, but also there are different alloys. So to that we add different alloys. That is iron, cobalt, nickel, and iron, nickel. Now iron, nickel. Okay, so these are the different materials that are ferromagnetic at room temperature. Obviously, if you take almost any paramagnet, you should be able to get an ordered state at low temperature, but you should keep in mind that it depends on the interactions, because if you have a paramagnet with negative Curie temperature, even cooling down to 0 temperature won't get it in the ordered state. Okay. So these are ferromagnets. So if you look at the ferromagnets, then the neighboring magnetic moments are aligned. They are aligned and pointing in the same direction. Now we will look at the antiferromagnets. Antiferromagnet implies that we have a lattice with the magnetic moments aligned in the opposite direction. This software allows me to draw very straight lines. Okay, so antiferromagnets, we already looked at those. The examples would be chromium, manganese. At room temperature, they are ferromagnets. Now let's look at the susceptibility, how it depends on temperature. For susceptibility, again, I'll use this handy tool. So that would be temperature. This would be chi. Again, if it's a ferromagnet or antiferromagnet, if you heat it up to destroy the interaction or to overcome the ferromagnetic interaction, it would behave as a paramagnet. So therefore, as for ferromagnets, there would be a temperature. I wouldn't call it theta in this case. I would call it Tn. And N stands for Néel. So that's Néel temperature. And this is a scientist who worked on the theory of antiferromagnetism. So in 1932, that's almost 100 years ago, he came up with his law that he describes the antiferromagnetism. So above this temperature, we have a paramagnetic state. So this is a paramagnet. Now below the temperature, we get antiferromagnetic ordering. So basically neighboring spins are pointing in the opposite direction. And here, it really depends on the rotation, but let me draw this thing. So that was something that he was looking. So this is antiferromagnetic state. Now, if you would like to describe the susceptibility, similarly to ferromagnetism, it's quite handy to plot it. This is inversely proportional. This plot is proportional to 1 over c minus theta. And we will talk about this sign, so we'll change that a little bit. But if you plot an inverse susceptibility, let me draw it slightly different. Let me draw it by hand. So we go like this. Oh, nice. Temperature, 1 over susceptibility. Then, first of all, until a certain temperature, which we call Néel temperature, we will observe a straight line. It's a straight line. And actually, the corresponding Curie temperature would be somewhere here. No, that's Curie temperature. So corresponding Curie temperature is negative. And the Néel temperature is the temperature which would happen. So it would point towards the negative Curie temperature, and then there would be a ray somehow. So if you write down the Curie Weiss law for this case, then with a negative Curie temperature, we'll write it down this way. So that would be susceptibility equal to constant divided by T plus theta. So plus here implies that we have T minus negative theta. So we'll use just an absolute value for Curie temperature. And in this case, it's important to understand that this value theta is negative. Okay, so antiferromagnetic state. So negative Curie temperature, as you recall, let me scroll up to remind you. Negative Curie temperature. So negative Curie temperature is molecular field opposes external magnetic field. So this is what is happening in antiferromagnets. So with a negative Curie temperature, molecular field HM opposes external field. And well, let's do this. And again, I would like to note that this molecular field concept, it's an effective field. Now, if you go into bulk material, then this is an image in 2 dimensions. We'll have antiferromagnetic ordering, so you can see that neighboring spins in this direction and in that direction are antiferromagnetically ordered, so up, down, up, and here we have up, down, up ordering. So this is an antiferromagnetic state with anti-parallel alignment. Okay, now let's talk a little bit about materials. As for materials, I will use a text tool and I will type. So we will have material, hold on, I will increase the font size so you would see what I'm typing here. Oh, let's use even greater than that, bigger font. So material and nil in Kelvin. So first of all, oxides, manganese O, manganese oxide, 122 Kelvin. The next one is iron oxide. Oops, iron oxide, 198 Kelvin. Cobalt oxide, 293 Kelvin. We are getting closer to the room temperature. Then nickel oxide, 523. Then chromium oxide, chromium 203. That is 307. Iron sulfide. So iron S is 613. Chromium 310. So you can see that there are many materials, and we already looked at chromium. Now I can remind you, if you remember, there was this Bethe-Slater curve. So we had drawn it before. So this is exchange integral, and this is as a function of 3D. So this is interaction constant, exchange constant, as a function of atomic radius ratio to the radius of 3D orbital, and that is the curve. It goes up and down. So we have ferromagnets here, ferromagnets, and that's interesting. I wrote ferromagnet, but I can write it's iron actually here. And ferromagnets are for this case, so J greater than 0 is ferromagnets. Now there are others, nickel and gadolinium, but if you look in here, there would be manganese and there would be chromium. Obviously, stronger the interaction is, stronger the ordering is, higher the anneal temperature. So you can see that the interaction, so if you look at the manganese oxide, and we'll talk about this specific material closer to the end of this lecture, then that is fairly low temperature in Kelvin. So room temperature is, if you remember, so let me write it down. So room temperature is approximately 300 Kelvin. So you can see that if you cool down to, I don't know, slightly, make it slightly chilly in the room, air conditioning, your cobalt oxide will get ordered into the antiferromagnetic state. You need to cool down to much lower temperatures in case of manganese oxide, iron oxide, nickel oxide. It actually is antiferromagnetic at room temperature, and you have to heat it up to 200 degrees Celsius above room temperature approximately to get it. So chromium 203 is antiferromagnetic. Ferrum S is antiferromagnetic at room temperature, and you have to heat it up significantly to get it into a paramagnetic state. Chromium as well. So these are the materials. Now, there are many more other materials that can be ordered in the antiferromagnetic state. But let's look at why things are, how we treat this, how we basically deal with this. So what we will be doing is the following. So this is your antiferromagnet. Let me draw it. So antiferromagnet, and it continues this way and that way. Let's take a, just for simplicity, for my ease of drawing. So we will do the following. We will say that, okay, let's have this system, but let's consider that we have one lattice with magnetic moments pointing up and the other lattice with magnetic moments pointing down. So this would be the other lattice with magnetic moments pointing down, and this would be the first lattice. Let me make it also colored green. Okay, so two lattices. So that would be sub-lattice B in red, so these magnetic moments pointing down, and this one would be sub-lattice A. Okay. Also, we would allow interactions only between nearest neighbors. So basically, our A only interacts with B. A does not interact with another A. Let me draw A. So there is no interaction with A. There is interaction with B, B with A, and etc. And there is no interaction B to B. So we interact only neighboring interactions and ignore A to A and B to B. Okay, so now to describe this, we would use also molecular field approach. So we would have a certain molecular field responsible for ordering of spins A. And as you see, we have interactions between A and B. So basically, the effective field that would define interaction, that would define ordering in this case, would be the field that we would have to use gamma MB. And similarly, HMB can be written as negative gamma MA. So negative sign. Molecular field is opposite to the magnetization of the other sublattice. So that's why we have the negative sign here. Okay, so with this, we can now look at different cases of molecular field. We already look at this. So if we plot, and this is, again, I'm going back and forth. So as a function of temperature, 1 over chi. So we might have positive Curie temperature, and I will now write Tc, Curie temperature. And that would be, you can answer that on your own, but we're not in the classroom, so that would be the ferromagnet with a positive Curie temperature, T, and that would be ferromagnet T greater than Tc. Ferromagnet at low temperature, but at T greater than Tc, it's ferromagnet here. Here, this is a paramagnetic state. So for paramagnetic state, our molecular field would be greater than 0. Now there can be this case with a temperature that is less than 0. And if you look at this, I will modify it a little bit. What would happen is that basically we won't be, oops, no, that's too much, small eraser. Yes. So what would happen is that at this case, at this point, if it is antiferromagnet, the it would start to go up as we saw above. So let's scroll up right here. So this is the case. So you can see after when we lower down temperature below nil temperature, the susceptibility, inverse susceptibility starts to go up. Let's get back here. So this would be somewhere here, would be our nil temperature. And this is antiferromagnet. Antiferromagnet, and see the Curie temperature is below 0, less than 0, so molecular field is opposing this, opposing the external field. Now there is another case. I will actually use red for that. So would you guess what this case is? I don't see what you're thinking now while listening to this, but 0 Curie temperature. 0 Curie temperature, if you go back to the lecture on the paramagnets, there is no interaction between magnetic material, between magnetic moments. So this is the paramagnetic state. Paramagnet, ferromagnet, antiferromagnet. Let me make it look messier. Oh no, it's too good. Okay, so for paramagnet, the molecular field is equal to 0. All right, so that is our sublattices. Okay, so now let's look at different cases. So let's look at the case when we are above nil temperature. So there would be this area above. There would be, let me choose different color, this area below nil temperature. And there would be, which color to choose? This one. There would be exactly the nil temperature right here. So this would be our 3 cases that we'll look into. So case number 1 would be low temperature. So low temperature, let me do this. So T is less than Tn. And let me use the same color to highlight it. So we are below nil temperature. So what is happening? First of all, if you look at the sublattices A and B, they're pointing in opposing directions. And the magnetization, everything is ordered, which means that we are in the antiferromagnetic state. So the total magnetization M is equal to M of lattice A plus M of lattice B. And MA is equal to MB. That is an ordered state. So at temperatures below nil temperature, at temperatures, no, I want my ugly ellipse. At temperatures below nil temperature, we have a spontaneous magnetization. We have a spontaneous antiferromagnetic ordering. Now, if we plot the magnetization as a function of temperature, what is happening? Total magnetization. I wrote down here it's M plus MA plus MB at these temperatures, but you need to remember that this is actually a vector sum. So for vector sum, actually what we need to, either we need to put vectors in there or we have to put a negative sign here. So in this case, the total magnetization, they're equal and pointing in the opposite directions. So what it means is that total magnetization would be 0. But if you plot them separately, then this magnetization would be ferromagnetic. Oops, let me do a better job. And it would look the same for the other one. And to be consistent, let me highlight it. So A is green, B is red. So I would take red for B. So that would be our B. And this would be for our A sublattices. So this is A, and that is B. Correspondingly, this would be M sublattice A, and that would be M sublattice B magnetization with negative and positive here. A points up, B points down. Now, as in ferromagnetism, as we increase temperature, the thermal fluctuations destroy the magnetic ordering, and it comes to absolute zero at nil temperature. So if you measure magnetization of antiferromagnet and just plot magnetization as a function of temperature, it would be zero. It would be zero everywhere, below and above nil temperature. But at nil temperature, what is happening is that your sublattices become magnetized, and you have positive and negative magnetizations for this. Okay, so then this is below nil temperature, and so let's look at what's happening above nil temperature. So T greater than nil temperature. And this is above is yellow, so I'll use yellow color to highlight it, so you'll see it. I don't know, somehow it's thinner than I thought. Let's make it thicker. Yeah, okay. So above nil temperature, it's a paramagnetic state. So susceptibility, the definition of susceptibility, it's M over H. And also it follows the Curie law, C over T. M is H, C over T. Now let's apply it to sublattices. So MA would be some C, which we don't know. So that would be C, some prime factor, and H minus molecular field, gamma MB. Remember, for negative Curie temperature, molecular field opposes the external field. And molecular field for sublattice A is negative gamma MB, because it opposes. Now this is over the temperature. Same way we can write it for MB. MB is C, I write prime because it might be different from C, H minus gamma MA divided by T. Okay, so what we can do is we can look into the magnetization. So we know MA, MB, we can find M. So to find that, we have to calculate M equal MA plus MB, keeping in mind that they are opposing each other. That would be C prime over T. So here we'll have twice H minus gamma MA plus MB. All right. So now MA plus MB, this part here, this is this portion, right? So we can use and say that this is the total magnetization. total magnetization. So now if we solve this, so magnetization, let me highlight it. Magnetization equal to this minus gamma this. And if you solve this for magnetization, you'll see that magnetization is equal to twice C prime H divided by T plus C prime gamma. Okay, there are a couple of things here to notice. So that is the magnetization. Now let's find susceptibility. I'll keep it here. Susceptibility, chi, is M divided by H, right? So we take this M and substitute there. Substitute there. Yes. So that would be the same value divided by H, 2C prime T plus C prime gamma. All right. So you can see it has the form, and this is the reason why I used prime C here. So it's equal to C divided by T plus theta. And of course, it's important to understand that theta here is less than 0, Curie temperature. Okay, so what we did, we assumed that we have an antiferromagnet. Let me recap that going up here. So here's our assumption. We have a antiferromagnet with two sublattices, sublattice A and sublattice B. Sublattice A interacts with sublattice B, but sublattice A does not interact with itself. And assuming this, and use the molecular field approach, Weiss theory basically, we derived the susceptibility and we derived the Neal theory for that. So we have susceptibility equal to C over T plus theta. So it's important to understand that this susceptibility dependence, if you recall, so this is this part. This is Neal temperature. So that describes only the paramagnetic state, and also it describes, and this is something to remind, so this part, you see, T is greater than T Neal, so it's a paramagnetic state of the ferromagnet. Okay, now what we will do now is this purple thing, T equal to Neal temperature. So T, what happens at Neal temperature? At Neal temperature, and let me highlight it with the color I used for that one. So again, let me choose a bolder. Okay. No, this. So at Neal temperature, let's consider that let H external is 0. Now, if you look at this sublattices, so let's look at this, for example, for MA. So this one. So for sublattices, MA is equal to C H minus gamma MB divided by T. And this is we do not care if it's above or below. This is just an expression. Well, at Neal temperature, there are a couple of things happening. First, we'll have external field equals 0. Second, T equal to Neal temperature. So MA equal to C prime H minus gamma MB divided by T. So we do Neal temperature N, and we also take this and let it equal to 0. H equals 0. So what it gives us is C prime J MB divided by Neal temperature. If you look above, this part here is Curie temperature, theta. Let me show you. This part here. This is Curie temperature. So we can write that magnetization A, MA, is equal to minus theta MB divided by nil temperature. Okay, what do we know about MA and MB? Remember that MA is equal to minus MB. It is the same magnetic moments. They're just pointing in the opposite directions. So if you take this into account, what we will get is we will get that theta is equal to Tn. And that works. So theta equal to Tn, and this is a Weiss, using Weiss theory for antiferromagnets. So in real experiments, so if you look at this, let me go back. So this is messy. Let me go back to here. So this is a nil temperature. This is a Curie temperature. So they're supposed to be equal in theory, but in general, in experiment, theta is always bigger than nil temperature. And if you take, well, it's not quite a good comparison, but in general, so if you look at this, so this is nil temperature is lower than the Curie temperature. This is experiment. So let me write it down. Experiment. Theta is greater than Tn. Okay, so now also, if you look at the susceptibility. So susceptibility in the antiferromagnetic state. So let me get my antiferromagnet here. So this is antiferromagnet. So it turns out that susceptibility at T less than T nil. And let me again go to, I apologize for this fast scrolling. We are looking at this green part. Well, it's important to understand. Let me fix it a little bit. So I'm fixing medium eraser. No, I'm using medium eraser and erasing this. It's important to understand that we are dealing with not negative temperatures, but we are dealing with this part here. And this part here, actually, if I scroll up to the graph, this one, it corresponds to this part here. Basically, we are looking at the area, or this part here. We are looking at the area below nil temperature, but we still have to stay above zero. There is no temperatures below zero. Okay, so here we are. So chi, susceptibility at these temperatures, what is happening? It turns out that susceptibility actually depends on the angle between the direction of spontaneous magnetization of the sublattice A and B and the direction of applied external field. So what it means is that imagine that you cool down your antiferromagnet like this, and you cooled it down. Let me see if I can rotate it. No, probably not. Okay. And it magnetized this way. Then, if you apply your field this way or that way, you'll have different values of susceptibility. So this is another example of anisotropy. another example of anisotropy. So when we apply magnetic field parallel to the magnetization, we will call it H parallel, and corresponding susceptibility chi parallel. And following the same notation, this would be H perpendicular and chi perpendicular. So there are two cases here. So let's start with case number 1. H is parallel to spontaneous magnetization. It is important to understand that this is spontaneous magnetization, so it can get ordered in one way or another. Okay, so when we get into the ordered state of spontaneous magnetization, our lattices, sublattices MA and MB, they magnetize, they both follow the Langevins. Or there is also Brilliant. This is Brilliant theory. So I would refer your C lecture on paramagnetism. Yes. So in this case, if you remember, yeah, good. If you plot, there is this factor N, M, L as a function of alpha. This is too thin. Yes, and as a function of alpha. I would refer to the lecture on paramagnetism on Langevin's theory of that. There would be a Langevin's function that would go like this. And alpha, to remind you, is alpha is mh over Boltzmann kBt. And this is basically our magnetization. So as we apply magnetic field, our material gets magnetized following this Langevin's function. L alpha is Langevin function. Now let's, if you apply to sublattices, so what's happening when you apply field? So remember, you have sublattice A, that would be A, B, A, B, etc. So when we applied field, and let me apply it with a different color, we imagine that we apply field. First of all, the field is parallel. This is the case. Field is parallel to the spontaneous magnetization. So we apply field in this direction, pointing, let's say up, doesn't really matter. Magnetic field. Then what would happen is that field would introduce small delta MA in this direction, and also it would introduce small delta MB in that direction. So in this case, MA would point along a magnetic moment, and MB would point in the opposite direction. So this is so if you write it down mathematically, so what would happen is that we will have MA M sublattice A plus delta MA, and we would have MB minus delta MB. So here we added, here we subtracted, because magnetic field points in that. Now what would happen if you look at the magnetization? That would be MA minus MB, taking the sign into account. That would be delta MA, absolute value of that, plus delta MB. So if you substitute these. So what is happening, you can relate it to you can relate what's happening. So if you have variations, then delta alpha, this alpha, we would have, first of all, m over kt, and variation of the field. So if you apply small field delta H, let's add delta here, delta. So now if you look at that, so that is this, and that can be written as m over kt H minus gamma delta mb. A is already magnetized along that direction, and all we do is we change B and we add it to A, delta MB. Now this is delta alpha, and if you look at this plot here, so for example, we are sitting somewhere here. Let's say you are here, and that's your, if you look at, for example, MA. MA would be the magnetization. This is error, that's not alpha. Then by varying the magnetic field, we can either increase it, and that would be plus delta, or we can decrease it, minus delta. Now this is some alpha naught. Okay, so what's happening is that basically our susceptibility, in this case, the magnetic susceptibility, we can look at the magnetization. So if you go back to a lecture on paramagnetism, you'll see that magnetization is equal to number G factor total angular momentum Bohr magneton, and there is this B J of alpha. So Bj of alpha is the Brilliance function. Bj, oh, let's write J here, and let's write of alpha here. That is a function that basically is related to Langevin's function. It can be written as 2j plus 1 over 2j hyperbolic cotangent of 2j plus 1 over 2j alpha minus 1 over 2j again hyperbolic cotangent alpha to j. So it's a Brilliance function, and basically the Brilliance function defines the magnetization. So if you look into the magnetization as a function of alpha, that would be this function. And you have, if you don't apply alpha, is related to the magnetic field. So this is basically part of our hysteresis curve. So if you recall HM for paramagnet, it looks like this. And so this part is basically the dependence of magnetization on the field, and it's defined by the Brilliance function. And Brilliance function is this. Oh no, I don't want this, I want that. Okay, then if you know magnetization, we can divide it by the field, and if you divide it by the field, we'll get our susceptibility, chi parallel, and that's parallel to the magnetic field. In this case is 2n m square Brilliance function j alpha divided by 2 kt plus n m square gamma, Brilliance function J alpha. So if we plot this, so this is, remember, we are looking at T less than nil temperature. If we plot this, T susceptibility, then above nil temperature, that's our Curie Weiss law. That's basically Weiss theory. This is nil temperature, but we are looking at this susceptibility at temperatures below nil temperature, and it is going down to zero here. So it goes down and all the way to absolute zero. So as temperature goes down, susceptibility approaches zero. So it's and actually it's not zero, but thermal fluctuations. There are no thermal fluctuations at zero. It's supposed to get to zero, and we have ordered state. So this is antiferromagnetically, this is antiferromagnetically ordered state here. So now, also it should be noted that if you remember, we have H and M. They are pointing in the same direction or opposite direction. If you remember, torque applied on the magnetic moment, M cross B. And in this case, magnetization and magnetic field are parallel. So in this case, torque is equal to zero. So torque is zero, and A and B lattices stay aligned. So we do not apply any torque, they stay aligned parallel to each other. And of course we can break that alignment by applying huge magnetic fields, but still we are not applying any torque. There can be thermal fluctuations too. Now let's look at the second case. So second case is H perpendicular to M. So when we apply this, so imagine now, let me plot this sublattice A, MA, and let me use the same point of the vector, and that's MB. MA and MB. We are applying magnetic field, we are applying magnetic field perpendicular. This is H to both lattices. So now, in this case, we are applying torques. We are applying torques to both MA and MB, and what's happening, they start to tilt. They tilt on the same angle. So we are applying field, we are inducing magnetization, and therefore we are inducing, there is a molecular field. So at equilibrium, molecular field is balancing external field. This is at equilibrium. So field is equal to the molecular field is equal to twice molecular field of, so let's say, sublattice A sine theta, because we are looking at the component of this, so that would be the component of the field. So molecular field sine theta, that would be equal to 2 gamma MA sine theta, which is actually our gamma M. And susceptibility perpendicular component would be M over H, which is 1 over gamma. See? Field is proportional to the magnetization, and it basically is because it's a molecular field. But 1 over gamma is constant. So what it means is that when we apply magnetic field, if you apply magnetic field perpendicular to sublattices, then two sublattices would just tilt, and the induced magnetization would be proportional to the magnetic field. So what it would mean is this. Let's plot it. So this is nil temperature. We have paramagnet on this side. And after that, we will have a flat curve. And that would be for perpendicular, which is constant. Now, if it would be parallel, it would go down to 0. Chi parallel. Okay. Now, when you have a material, how you would know if you're measuring it parallel or perpendicular to the lattice? Well, as you rotate to the other direction, so it would be magnetizations anywhere in between. So if you're measuring powder with random distribution of crystals, then you would have something that goes down to here, and that would mean it's not perfectly aligned with the magnetic field, so your lattice is not aligned. So now let's take a look on one of the examples. So I took this example from the scientific paper. So here is this paper. It's a PhysRev paper by these guys, published there. So they're modeling ferromagnetism and paramagnetism phase transition. And in this paper, there is this graph that I will show you. This is the graph that I will use. So what these two authors do is they model the transition, and you can see that this is the nil temperature, and nil temperature here is, if you look at it, nil temperature is approximately 80 Kelvin for this material. This is the paramagnetic state here, and this is antiferromagnetic state here. And the dependence of susceptibility on temperature in the antiferromagnetic state would depend on the orientation. So you can see that there is this portion with a susceptibility perpendicular, field perpendicular to the sublattices, and this section here where the susceptibility is parallel to sublattices. As I said before, then in samples with a powdered, let's say powder sample, what is powder? Powder is not a single crystal. You have, like sand, you have many crystals with a random orientation of magnetization. So some will be perpendicular, some will be parallel, some will be random. So for those samples, the susceptibility is somewhere in between, somewhere here. Let me draw it once so it won't be doing this. So this is susceptibility of the powder. So it's also important to understand that once we are above nil temperature, we will have the same paramagnetic state. Now this is plotted for the manganese oxide, and manganese oxide is antiferromagnet. Other thing, so why our HM, why the molecular field is negative? So HM, we say, is negative. So this, to understand this, you have to recall the origin. Origin of HM is exchange interaction. And exchange interaction, energy of interaction, minus 2J SI as J. So J is our exchange constant. So for ferromagnet, J is greater than 0. For antiferromagnet, J is less than 0. So that is the origin of molecular field. Now last thing I would like to talk about is a very interesting case for the exchange interaction forming manganese oxide. Manganese oxide. So manganese oxide has ionic bonding. For ionic bonding, it means that we have manganese 2 plus, we have O2 minus, we have another manganese 2 plus. So in manganese, that is our 3D orbital, and it is in the state of 3d5. So 3d5 has 1, 2, 3, 4, and one more, 5. And the same here. 1, 2, 3, 4, 5. So these two. Now for oxygen, we have unfilled shell, that's a p orbital. I will draw it schematically here, and we have electrons. So we have this spin down. No, let me choose a thicker pen. So we have spin down and spin up. Okay, so what happens, this is ionic bonding. So what makes the bond, basically the electron from here gets transferred to manganese electron. An electron from here gets transferred to manganese as well. And that forms the ionic bond. So obviously we cannot put another electron pointing up in this shell. So this electron spin down gets into this shell, spin down. Now if you look at this, this is the other electron has spin up, so we cannot put it there, but it is spin up. So it does really go there, which means that the rest of electrons should change their mind. So this is our spin up state, and that defines the orientation of other electrons there, and they are pointing down 1, 2, 3, 4, 5. And if you look at this manganese has magnetic moment pointing up. This manganese has magnetic moment overall pointing down. And that is basically a antiferromagnetic ordering. Spin up, spin down through the oxygen. So they do not interact directly, but there is exchange interaction between manganese oxygen and another manganese. So this type of exchange interaction is called super exchange. Super exchange, and that what defines basically the magnetic ordering in oxides, in most of those, where interaction goes through the oxygen. Okay. So this is the end of the lecture on antiferromagnetism, and we will have more lectures, so keep in touch.